So last time I was I introduced the Bloch-Levin tower, and I want to recall this quickly and and also introduce some improvement in the construction. So and this improvement will be essentially based on the following definition. This will give us a way somehow to remember some of the functionality of this tower. So I call a leveled scheme simply let's see, Noetherian scheme X with a locally constant function and x goes from x to the integer. Right. So if x is connected, this is simply just a relative an integer. So then the interesting thing is maybe rather the notion of morphism of leveled schemes. So I say a morphism of leveled from y to x. It's a morphism satisfying the conditions. So there's a morphism. Morphism such that the following inequality holds for every such that for every point in big Y, x the image, we have that codimension of the point, small x in big X, minus the value of this function at the point is smaller than the codimension so we okay, and so these form a category, and I will denote this by these which I denote by scheme K leveled. Of course, I will often consider subcategories of some. For instance, I will take on a scheme of finite type, then I put ft here. Okay, so yeah, and so the point is that the Bloch-Levin towers are naturally towers of complexes of presheaf on this category. Tower of complexes presheaves on finite type leveled scheme. And so maybe I think it's maybe a good idea to remind you what is this Bloch-Levin tower. So before going on, let me just quickly redo the construction. So what we do is we start with f, a complex of presheaves on finite type scheme over a diagram A Pn. now I fix an integer p, and also let's fix a subset, finite subset of n, and let's also fix a schema finite type, which is leveled. Okay, so and so with this notation, I'll denote. So I'll define a complex BL pi f at x, evaluated at x. So this will be by definition. So motor prelimit over subset k inside G inside I of the following thing. So f, the value of f at this pro-open subset. And now what I do, I take, so I remove closed subset of codimension bigger than p plus n plus an x plus 1. So this. Okay, so and with this definition, this gives a complex of Prishev BL pi f, which lives on finite type schemes, which are leveled. Okay, and from this, so this gives a contravariant functor from, so this thing that takes E and give you BL pi f. Even if I look at the tower when I vary p, this is a contravariant functor on Pn, and from this, the usual construction give me a total complex, which I denote by BLP f. And so this is also denoted by BLF, and this is the Bloch-Levin law, which is associated to f. What is nx? Nx is always so it's part of the data. So
but it should be a number. Right?
yeah, it's a function.
Okay.
I mean, it's a function on the connected component of x. I mean, just think about it as a number. Yeah, it's a number. Okay, and so it's just somehow we it's entered in the definition here, and so the point is that if I restrict to morphism satisfying these conditions, then this becomes functorial in X. Okay, otherwise it's not functorial in X, because I mean this open subset. If I just put a UP is not a functor in X. Okay, I mean think about a closed subset in X. UP of this closed subset will not be in the UP of X. Yeah. But if I put a level somehow like this, then it becomes a functor. Now this expression becomes functorial in X, and then it defines a functor or a presheaf on. Okay. So here's a remark which I will use later. So if you have f a presheaf on let's say finite type level scheme, then there is a way to associate to this a presheaf on just finite type schemes, and it's very simple. So we define. So I denote this by AF. So this is AF a presheaf on finite type schemes by setting so the value of AF at x. This is the colimit over all integers of fx comma n. And so I put I take the function n constant on x, then this makes sense. And if you increase n, there are obvious map from xn plus 1 to xn, and you take the colimit of this. And somehow, and the point that so since every morphism of schemes becomes leveled if we take something like this for n much bigger than m, then it's easy to see that this definition gives indeed a presheaf on finite type schemes. Okay, so this is a general construction. Now let's maybe let me just say how this will be used. I mean, what is the natural thing to do in the case of this tower? So maybe another remark. Let's continue it. So let now be f as in the construction. So there are natural maps, for instance, from, so let me maybe write them. So we've defined, in fact, several or three type of construction on F, and there are maps like this. So these are complexes of presheaf. This is a tower of complexes, but if you think about it as a constant tower, then there is a map of towers like this. So this is, if you want, it's, yeah, this is a sequence of morphisms of towers of on finite type leveled. Now, if I want to get something which is really just on finite type schemes, I can do the following. So I can take in fact the limit, maybe even the homotopy limit over P. Okay, so this is this makes sense. Now this is a morphism of presheaves on here, and then I can take the associated thing. Okay. Right, and now this is just the honest morphism of presheaves on smooth on finite type scheme over K. Okay. So in some sense, one should think about this as this guy here is some kind of a completion. So this is, if you want, a conival completion. Completion of F, or maybe pi of F. And I should maybe also say that it's very important to first take the homotopy limit before applying A, because it's clear that if you apply A on each of so if you apply A on BLPF for a single P, this will be 0, obviously. Okay, so it's good. It's important that first one take a homotopy limit before applying this A. And yeah, maybe I should say also that, yeah, in fact, this A here is not really important because this, how to say, so this, so I want to say this because it will come later. So here, so the colimit defining, so the colimit defining A of this is in fact how to say, is stationary. I think it's still on the black. Yeah, it's still here. So if F is this homotopy limit thing here, then the map defining the transition map in this colimit are actually all quasi-isomorphism. Yeah. So it's not. There's not really a serious colimit going on here. It's just yeah. It's a colimit of, and the transition map are quasi-isomorphism. Yeah, I mean, this is important because later I will have to, so that there will be a homotopy limit here that I want to put A here. So it's going to be useful later. Okay. All right. So what I want to do next is extend this construction to the case of double star schemes. But before doing this, I want to discuss a little bit the so-called the block moving lemma in a slightly generalized context. So this will be a generalization of blocks moving lemma. Which I think I mentioned last time. Okay, so I first introduce a couple of definitions. So, okay, so let's take X to be finite type stratified scheme over base field. So we say that X is toroidally stratified. So we have seen before the notion of regularly stratified. Now this is a slightly more general notion. So if locally on X, that you can find a tal morphism so going from X to T bar, where so T is a split torus, and T inside T bar is an equivariant embedding. and such that the stratification of X is is obtained by pullback, or is a pullback of the natural stratification on T bar. Of course, by orbits. So T bar is stratified by the orbit or the action of T on T bar, and the stratification of X is just given by the pullback of the orbits. So this, of course, it's kind of a classical notion. No, I don't assume this. So this is essentially classical notion, which usually people would probably say that x0 inside X is a toroidal embedding. Maybe you assume, I mean, yes, I think maybe some people assume X to be normal when they speak about toroidal embeddings. I will not do this here. Okay. Yeah, so I have this remark here, but which is maybe not very useful, but let me still giving this. I mean, it's useful for some proofs, but since I will skip most of them, it will maybe not be used explicitly later today. But nevertheless, maybe it's good to say this. So let me take X to be toroidally stratified and normal. So one can do something which we actually have seen in the case of regularly stratified schemes. So if I take a stratum C, so we can associate the following object. So I'll denote by VXC. This will be the smallest constructible open neighborhood of C. Then I denote by RXC. This is the lattice of Cartier divisors. Of constructible Cartier divisors. On VXC. And so this has a submonoid consisting of the effective ones. So this is our effective Cartier divisors. Okay, so we also consider the dual lattice RXC Also, consider the real vector spaces Rxc and similarly and then there is this associated cone, which is denoted by sigma xc, and this is defined to be the x. So this is a cone in the dual real vector space. So x in R exc, such that when you take the pairing of Vx, this is positive for all V effective. Okay, so this is a rational convex cone. Okay, and then so the collection of these convex cone with the obvious relation between them. So for instance, if C is contained in the closure of some other stratum D, there is an inclusion between. So then this the rational cone associated to D will be a face of this one. So there are some inclusion between these cones, and the collection of all these cones and their inclusion. This is something that people call a conic polyhedral complex. Which is associated to X and is denoted by delta X. Okay, so this is it's something which is associated to X, and it's actually it's a useful thing, because then we will be able, one reads somehow some construction on X from construction on these conic complex. And so we will see one of this in a moment. So. Okay, so these considerations are important when we speak about toroidal modifications. Let me first explain what is a toroidal modification. So we start with X toroidally stratified, and so a toroidal modification of X. So this is a morphism X prime to X, which is proper, and which is locally obtained by pulling back the Ital morphism from morphism of torus embedding like this. So you have a split tori which is inside and two compactification and proper morphism between them. Okay, so this is it's actually maybe a definition. And now the remark is that so if x is normal and x prime, and you only so if x is normal, then that is a one-to-one correspondence between normal toroidal modification and so-called finite rational subdivisions and finite subdivisions of delta x. And so yeah, so if x prime will also so this map will induce a map from delta x prime to delta x, and this map will be just a subdivision of the polyhedral complex. Okay, and there is a one-to-one correspondence between these two things. Okay. So I also need the notion of toroidal morphism. Okay, so here I take x and y two toroidally stratified schemes. So toroidal morphism from y to x. So is so it will be stratified, or it will be morphism of stratified schemes. But let's just is a morphism which is locally of the form T bar prime to T bar, and here again T bar and T bar prime are equivalent embedding, except that we don't ask that this is an embedding of the same torus, so the torus will be different. But we so instead we ask that this map here is surjective. Morphism of tori. And so we say that y to x is saturated if we can choose these maps such that T prime to T has connected kernel. All right. Okay. Still one definition more. So now let's take V to be a polytray. Endowed with its finest stratification. Okay, so I want to define the notion of toroidally stratified V scheme. X. So what is this? This is a finite type V scheme, a stratified which is isomorphic or obtained as follows. Obtained as a fiber product like this, where so B is a regularly stratified scheme of finite type. XB will be again a toroidally stratified scheme. There is a map from XB to B, and this will be toroidal morphism. Which we assume to be saturated and equidimensional. And finally, we have a map from B to B, which is dominant. Okay, and so of course, this is stratified by the fiber product stratification. Okay, so remark. So if x is as before, x over v as before, we can speak about. So there is a notion of toroidal modification. Of x prime, of x prime to x, which I will not spell out. I think you imagine easily what it should be. And these they form a category denoted by b of x. Okay. So this is so yeah. If v is a field and x is regularly stratified, this is equivalent or this contains a cofinal subcategory which is given by blow up of faces. This is what I was. This is something I think I mentioned last time. Okay, so this happened to be a co-filtered category. Okay, and now I can state this moving by blow up lemma. So as before, we take V polytre X toroidally stratified scheme. So let Z inside X be an irreducible closed subset such that the intersection of the open stratum with Z is has codimension larger than R, of course in X0. Then, so the conclusion is that there exists a toroidal modification such that the strict transform of Z meets every stratum in codimension bigger than R. So I will not prove this. Okay, but this is somehow this is. I'll tell you where this is somehow will be used later. Okay, so now I come to this the Bloch-Levin tower number 2. Part 2. All right. So let me recall what you want to do. So here we so the first Bloch-Levin tower I spoke about was concerning essentially the diagram of scheme A. Here I want something which somehow has to do with this diagram P double star. So let me first remind you that we have this this morphism of sites of big site on some diagram of schemes. This is P tilde. And this is pi. Let me still write it here maybe. So, okay, so we have this diagram, but we also have for every I. So if I fix I, then I have somehow a smaller thing like this. Now this becomes a constant diagram. So yeah, I'm using both. All right, so yeah, given F complex of presheaves on a scheme of finite type, we defined or a construction which I denote now by P upper star I of F. So this will be, it's a complex of presheaves on finite type scheme over the field, and it takes so yeah, it's given as, so let me write down again. Just taking two direct images and then applying this singular complex, which is remember this is responsible of this E bar localization. Okay, so this will be a notation for. So this construction will be denoted by P upper star I. Now, if F is over over the whole thing, even if I vary I, then the association sending I to pi upper star I Fi is a contravariant functor. And as usual, this can be used to get the complex pi star. Well, now this is a complex of pre-sheaves on finite type schemes over K. And this is just to remind you. So this is a construction that we have seen before, and now we want to modify this construction as I did in the case of scheme over of just single schemes. Okay, so there are two steps in the construction. The first one is where we blow up faces, and then where we remove some closed subset. So let me first it describes the blow up procedure. Yeah, over the thing that where P star. Okay, this is the big diagram. Okay, so I need the construction of some pro schemes. So here I start with X toroidally stratified K scheme, so just a scheme of finite type which is toroidally stratified. So I give myself S just a scheme, also of finite type. And so I want to define a pro scheme which, or first, so so I want to define, so we define a subcategory which I denote by B Sx. So B, of course, will be for blow up. Again, we will be somehow blowing up faces of X, but this will be relative over S. So this will be a subcategory of finite type scheme over the product. So as follows. So I'll give you the definition of this category. All right, so a scheme over this product will be in this category if the following hold. So I want, so So the map from y to s times kx to be proper, of course, and inducing and induces an isomorphism over s times the open stratum. And moreover, I want that the inverse image, which is the same, to be dense in y. Okay, so these are natural conditions. And then we want this somehow to be toroidal in some sense, a toroidal modification in some sense. So we ask the following. So there exists a morphism from S to some big affine space. A toroidal modification E of an times x, again, which is an isomorphism, which is an iso over an times x0, such that if I denote by if z inside the fiber product is the closure of S times kx0. So then there exists a map from z to y. So y is dominated by z. Okay. Okay, so I set a lemma which I will not prove, so which is not so difficult about this construction. So x will be as before. So we have the following facts. So unless S is empty, this BSX is cofiltered. Then it's also functorial in S. So if you have morphism S prime to S, there is functor of BSX to BS prime X. And it does the following. So it takes y to the closure of S prime times of S prime times x0 in the pullback in S prime. Okay, and last property is that there so if V is a polytray, there exists an inclusion between the category of toroidal modification of V times X, which is of course a toroidally stratified scheme over V, inside the 2 colimit over all maps from V to S of B Sx, which is cofinal. Okay, so as I said, it's not surprising or nor difficult. Just maybe mention one thing. You see, in the definition of this category here, that there is no condition on what's happening over this, right? So here we are always, I mean, here we always ask that over S times x0, it's the identity. Okay, I didn't ask anything in this here, but in fact, here it is automatic that every toroidal modification will be identity. Okay, so x0 is, I mean, x0 has no stratification. It's smooth without stratification, and the stratification of V times x0 is just by fibers. Okay, and if you blow up any of these fibers, you don't change anything because V is a polytray. Okay, so this is why this statement is reasonable. Sorry, colimit over all morphism from V to S, where S of finite type.
But there's some condition on the stratification.
No. I mean, there is no S is not stratified.
S is toroidal.
No. S is a finite type scheme.
Not
S is any finite type scheme. Yeah.
okay. Not
No, I mean, yeah, not as in 2. No, but I mean, the E is a toroidal modification. So in 2, I take a toroidal modification of AN times X.
I just can't read. Yeah,
Sorry, no. I mean, fine. So just let me say it again. So AN times X. This is of course toroidally stratified, and the product also. And E is a modification of this toroidally stratified scheme. But then the morphism S to AN is any morphism.
Not proper, not rational.
No. Any morphism, S to AN, any morphism. In general, it will be, I mean, yeah, just any morphism. Yeah. I mean, this is, of course, only reasonable if S is affine. But if S is affine, you can take close immersion. It doesn't matter. Yeah? I mean, the point is that you have this condition that it's over here, you don't modify anything. So when you pull back, it's kind of a reasonable thing without any condition on this map. So it's not so important. It's just one should think about this construction as a way of. I mean, what's really, I think, important is this claim here. So you should think about this construction as a way to approximate this category, which we are interested in, the category of all modification of this V times X by things which are of finite type. I mean, right, so with this, now I can introduce the following notation. So again, let's take S of finite type. Let's fix some finite an empty subset of the integers. Okay, so we denote by SA hat A. So this will be the pro SAI scheme, which is given by the inclusion of this co-filtered category B S. Okay, so it's the pro object of the kind of blow-ups in the previous definition. Okay, and and as before, I also denote by partial G of SAI. So this is the inverse image of the face. Okay, so this will play somehow the role of the hot the hot AI in the previous that we saw previously. Okay, and so we have the same fact as before, as in the previous situation, namely that we have a functor Qi to pro scheme of finite type over S that takes K inside G and map it to delta K G, sorry. All right, so now I can do the analogous construction of this pi hat. Okay, so the next The next will be, so is, the goal is to construct this phi star, which is the analog of phi hat that you have seen before. And it will not maybe be apparent immediately how this is the analog, but because first I will have to construct something slightly different, maybe, I don't know. Let's see. So here is the construction. So let me fix some objects. So here F will be a complex of pre-sheaves on finite type schemes over the diagram, and P star A, and I fix, so I fix an I for the moment, and then I let I vary later. All right, so so I do the following. Yeah, okay, let's fix the following data. So I fix an object in this category QI. I fix an alpha in theta bar omega I. Take an E bar alpha scheme of finite type S, and X a K scheme of finite type. Okay, so and then with this we set the following. So I define a complex, which is the following one. So I denote by phi. So depends on I, depends on K inside J. It depends on alpha, and it depends on S and X. All right, so what is this guy? But this is simply, you take the global section of some double star pro scheme, which is the following. So maybe, so it's a global section of course, of F alpha, and global section of the following object. So you have S, you have a map to S, and this is from partial K, this blow up relative to S, G, and times X. And then the next map goes to this similar thing, but without the S. All right. Now, so fixing everything, but except, so fixing everything, so except K inside J, we can do the following. We can define phi I F alpha Sx to be the homotopy limit over K inside G of the phi I K inside G, and so on. So F alpha Sx. Okay, so what is this guy? So this is a complex of pre-sheaves on a product category, namely the category of finite type scheme over E bar. I mean, this defines rather. So this defines over E bar times scheme of finite type over K. Right, if we let S and X vary. and alpha. Okay, so the complex of presheaves, which is denoted by phi I f. Okay, so the construction continues now. Okay, so we continue the construction as follows. So now I define phi tilde of I, and so indexed I, f alpha, and now somehow I get rid of the variable s in some sense. So and this is defined as the global section computed for the H topology of global section over E alpha bar with value in this presheaf that I obtained by just letting S vary. So this would be okay. So I fix everything except S. I get in this way a complex of presheaves over this guy here. And I just compute the H cohomology of E alpha with value in this presheaf. Okay, so this is a complex of presheaf on finite type scheme over K, but it's actually over K as a diagram. So over this thing here. Okay, and then we are almost finished now. So we define this guy to be, so this is a singular complex associated to gives okay, and then from here it's okay. Maybe let me So we have the following lemma that we have seen an analog of it last time. So here assume that F is HHH fibrant, then the obvious map is a quasi-isomorphism. It's proven similarly as the previous one. Okay, and so let me just write it here. So from the pi hat i's star, one gets as usual pi hat star. Okay, so okay. Good. So now the next step is to introduce holes in the previous construction in order to get this Bloch-Levin tower. But it's not. Yeah, one needs to define what is meant by closed subscheme of codimension bigger than R with respect to some certification in this context, which is not so clear how to do this. So let me do this now. Definition. So take S, again of finite type, X toroidally stratified. Let's take Y to S times X in this category of blowups. Let's also fix some fixed scheme L of finite type, and now let's consider a closed subscheme Z inside Y times KL. So we say that, so this is closed. So we say that Z has S codimension bigger than R relatively to the certification of S. I mean, it's only. I mean, in this situation, there's only one certified scheme, which is X. Okay, I don't define certification on S nor on Y. Just so we say that it has codimension bigger than R relatively to Sx if the following condition hold. If the following is satisfied. Okay, let me say what is the condition. Now the condition is the following. It depends. So say that for every polytray, V, every morphism V to S, every commutative square with R toroidal modification of the product v times x. For all these data, the subset R times y. So the inverse image of z in R. So this is inside R times L, has codimension bigger than R relatively to the stratification of R. Okay, now here R has a stratification, natural one, and we can speak about having codimension bigger than R relatively to this stratification.
Who's toroidal modification?
This guy here. So toroidal modification relatively to V. This was defined before.
It was toroidally stratified
Yes. V scheme, and then the notion of, I didn't define it actually, I said it in a remark that there is a notion of toroidal modification of V toroidally stratified schemes. I mean, it's not difficult to define this. Maybe if you want, I can do it. If you want to know what is toroidal modification of a V scheme, it's not so difficult. I mean, it's just essentially a pullback of a toroidal modification. All right, so with this, I mean, with such a definition, it's not so clear that that you have a good supply, or yeah, it's not. Of course, it's not an easy thing to check. I mean, this definition is not really very practical, but it turns out that it's actually essentially. I mean, it's a good definition. And the reason why it's a good definition is that we can prove the following lemma, which, of course, I will not prove, but I'll at least state it. So the lemma says the following. So again, let S be finite type, X, as before, toroidally stratified. Assume we are given. Assume we are given morphism V to S from polytre S, polytre V, sorry. A toroidal modification R of the product V times X, and a closed subset Z inside R, which has codimension bigger than R with respect to with respect to the stratification. So these are the data. Then we can find the following. Then we can find okay, so first factorization like this with S prime of finite type. We can find y prime in the category of blow up S prime x. We can find also z prime inside y prime of S prime codimension bigger than R relatively to Sx. And finally, and S prime times Kx morphism R to y prime such that H, what's H? Oh, I don't know why I called it H here. Such that H is a pullback of Z prime. Okay, so in some sense, what this is saying is that the notion of having codimension bigger than R relatively to S behaves well in co-limit, in limits in some sense. Okay, so it's some kind of an approximation result in some sense. Okay, so if you start with something over the limit, which is V, we can approximate it by something over S prime, which is of finite type. Yes.
Y prime?
Yes. Thank you. Y prime. Right, so because of this result, this is somehow essential. I mean, yeah, I mean, this is there might be some other definition of what is another reasonable definition, but at least this definition works because of the following, because of this lemma. Okay, so let me now introduce a notation. Again, the analogous of this we have seen before. So S as before, X also as before, Y in BSX. And for an integer P, I'll denote by UPS Y times K with some auxiliary scheme L. So this will be the pro-open whose complement has S codimension bigger than p plus 1 with respect to Sx. Now we are interested in, of course, in a special case of this. Okay, so here take S x of finite type. Not x is not toroidally certified here. I take p an integer, take I in Pn. With this we set, or we consider, I know we set. So or we look up as times x. So what is this? This is the limit in the category of pro object. So it's really not really. It's just a pro object. Indexed on y b s ai of the up s y times x. Okay, and of course for g inside I, we set, or we denote by ups partial g sa I times k x, the inverse image of the face, partial g ai. Okay, so now we have all what we need to introduce the Bloch-Levin tower. So again, I redo the construction once again. Just I think maybe it becomes easier to digest like this. So essentially, it's the same construction as the previous one, where we replace where we look at these pro opens instead. So we fix a complex of pre-sheaves f, as usual, on finite type scheme over E star. So fix chi inside G, QI, alpha here, S and E bar alpha scheme of finite type. And now I take X leveled K scheme, finite type again, and now I also fix an integer p. All right, so with this we set the following. Okay, so exactly as before, I denote by phi. Now I have to take take into account the p, but then it's the same as before. Of f alpha and the pair of scheme S and X. So this is again, it's just a global section function. So it's just a global section of some star scheme with values in f alpha, and you imagine what we have to put here. So we have S, then we have this open U P plus NX, now relative to S, of the boundary okay, and then maps this to the non-relative version. So this is, of course, exactly, I mean, this part here is what we have used before in the scheme case. Okay, and then the rest is as exactly as before. So I define phi pi I f alpha x sx x to be the homotopy limit over k inside G of phi p I k inside G. Same. So this is a tower. So when p varies, this is a tower of complexes of pre-sheaves on this product category, which is finite type E bar times finite type scheme, which are leveled. And again, also as before, I get rid of S by taking a derived global section. So and yeah, and so on. Let me take some place. Right, so this defines this phi tilde pi f. Let's see when p varies. This is a tower of complexes of presheaves on finite type schemes. I suppose it's now it's K and this indexing category. And so then naturally we define BL star PI of F to be the thing that you obtain by applying this singular construction on it, on phi tilde. Okay. So this is the tower of complex of presheaves on, this is a tower, oh, I forget, I should put leveled, of course. So this is a complex of presheaves on finite type scheme over a field. Leveled again. Okay, so this is the Bloch-Levin tower in the context of double star schemes. Okay, so then from this one deduce BLP without the I, and so this is what I denote by BL star, and this is the Bloch-Levin tower in the context of star schemes. All right. Good. So this is the end of this paragraph. Now I'll give an important criterion, which is the next item is really a crucial point in the whole story. So
Schemes are still now endowed with level.
yeah. So it's a power.
Are schemes with level?
Yes. It is. No. So this guy here. So you apply. So this is a functor. So this is a construction. You apply this to complexes of presheaves on finite type scheme over this big diagram without levels. But the outcome is a complex of presheaves on this category here, which has level. So there's no star levels. I mean, it's just you start with a complex of presheave on double star schemes, and you end up with a complex of presheave on schemes which have level. Okay, so it's in the context of star scheme, but the outcome is just a complex of presheave on schemes. All right, so now I want to explain this criterion, which so criterion for quasi-isomorphism. So the goal here is the following. So we start with a morphism of complexes of presheaves on one of these. I mean, on this category that we are interested in. So the big one, the big one. And what we want, so we want condition which guarantee that if you look at this, at the block-Levene tower at, let's say, level P, applied, so the induced map, the induced map is a quasi-isomorphism on a fixed X in finite type scheme with a level. Okay, so we fix a level scheme X, and we want to know when this map is an isomorphism at X, is a quasi-isomorphism at X. This is what we are looking for. This is, we want a criterion for this. And so I start with some definitions, some easy definitions. Okay, so let's take Q be a pro scheme, and V a polytray over Q. So that is endowed with a map to Q. So I say that V is generically integral over Q if the extension is algebraic, where of course psi is the image of the generic point. So just generic point goes to induces a so the image of the generic point give you algebraic extension. And we say that V is generic if psi is a generic point. So similarly, maybe I should take some place. Okay, so there is of course a similar notion for double star scheme. So similarly, double star polytray V double star over some pro double star scheme Q star is said to be generically integral, respectively if V double quotation and double interrogation mark is generically integral, respectively generic, over Q for 1, 1, 1, 0, 0, 1. So this is in the case generically integral, and in the case generic, it just asks us for 1, 1. All right. So here's a remark. So let's keep the notation as before. So assume that V is saturated and generically integral over Q. Then there exists W, again a polytray, which is saturated generically integral plus generic over Q such that V is a closed subset in W. Okay, so whenever you have a saturated generically integral polytray, you can extend it to one which is also generic. This is not true, so maybe warning, not true for star-star scheme, except under some condition, except if one, we assume that Q10 is already a polytray, and 2, we assume that the map Q11 to Q01 is flat. So under these two conditions, we still have the same fact. Okay. Okay, so we have the following lemma, which is not so surprising, nor difficult. So I say that because it somehow explained maybe the next result, which I will not prove. So we take Q star star as before, so a pro scheme satisfying 1 and 2 from previous remark. We also assume that Q11I, so if I as, so we assume that the QI have dimension smaller than some big integer n, so independent of I. Okay, so I assume also that, what do I assume? Yeah. Okay, so let m to n be a morphism of complexes of presheaves on finite type schemes over Q star star. Oh, yeah, bounded by something which is fixed. Thank you. Okay, so I take complex of presheaves on this. Then the global section is a quasi-isomorphism. If m v star to n v star is a quasi-iso for all v star star closed inside w star star with w star star generic and generically integral over Q star. Okay, so it's this is not a surprising fact. Just think that if you are interested in the cohomology of Q star star, you don't need to know your complex of presheave on every star star polytray. You only need to know this for those which are closed inside generically integral ones. Okay, so it's, as I said, this is not really surprising. Okay, so we will apply this to the Bloch-Levin tower, and see what we get, and then I'll state some again one of the main facts that we will use later. All right, so it follows essentially from the construction of the Bloch-Levin tower and the lemma that we have the following proposition. All right, so let's fix an integer levels scheme morphism as in the beginning of the paragraph. Okay, so then the map induced on the Bloch-Levin towers sorry, so I need to make F vibrant. And then let's just directly evaluate at x. So okay, so this is a morphism of complexes. Now this is a quasi-isomorphism. Is a quasi-iso if the following. So if f v star to g v star star is a quasi-iso. Okay, for every v star star in w star star obtained as follows. Okay, so obtained as follows. So what? How do you do this? So it's in 3 steps. So first, fix some g inside I in Pn, alpha in V saturated V saturated polytray over E bar alpha. Then we take Y, a smooth X scheme W11 saturated polytray, which is generically integral over the pro scheme UP plus NX V of this V A G times Y. Okay, so this is second. Now third, we're almost done. So maybe I need some. Okay, I can continue there. So omega star star is the unique generically integral polytray over the following diagram. So the diagram is, you take V, you take then UP plus NX. Actually, I don't, yeah, it doesn't really matter now to write this, but I mean, I don't need to put this U anymore because I assume that my W11 is already over this pro open. But okay. Okay, so it's not this. I mean, this proposition is not saying much. I mean, what it's saying is the following: is that if you are interested in knowing when the Bloch-Levin tower induces a quasi-isomorphism for some map F to G and the fixed X, then you only need to check that your morphism of complexes of presheaves is a quasi-isomorphism of over the polytray that somehow enter in the construction of the Bloch-Levin tower at X itself. And these are those somehow, the one that you get by, yeah, they are essentially generically integral over these kind of things, which is essentially clear from the construction. Okay. Right. So now somehow comes the next fact, which is really the important fact, is that so a polytray over this kind of things is very special, and I'll tell you in which sense it is special. So let me take some place. Okay, maybe erase here. Okay, so I need to state somehow the main fact. I need a construction, which I think we have seen before, but maybe not explicitly. All right, so let's start with this a double star polytray, and let's give ourselves a point in V11. So to this, we may consider the pro object n plus v star star xi, which is obtained as follows. So you write your v star star as a limit of regularly stratified double star schemes, and the xi becomes limit of stratum, and then you take the limit of the n plus of a stratum that we have defined before. Okay, so this is, this is actually, I gave a name to such structure. This is a toroidal star-star polytray. So I don't want to define explicitly what this means, but let me just say the following. So if you look, for instance, at the open stratum, let's say at V11, so what is this? This is simply a torsor. This is a torsor over some pro-torus over the point xi. And in fact, this guy here, n plus V11 xi, is some kind of is a compactification of that. So it's a partial compactification, partial equivariant compactification, which is over the closure of xi. All right, and as I said, I think we have I mentioned this before, is that in this situation we can complete the square in a universal manner. So this is so there is a universal way to complete the square, and the universal way I call this, I denote it like this. I put 0, 0. Okay. And so it's universal, and somehow, if you want, in the category of toroidal polytray, and yeah. And in fact, so if you want this square is pro-initial object in the category A V star star psi, which is defined as a two co-limit of what you think. Okay. Right. So with this notation, I think I don't need to say more. Yeah. Now I can state the main fact. Which somehow justify maybe the complicated construction I've been doing today, and maybe even all the complicated construction I told you about. So we have the theorem. So let V be a polytray. X toroidally stratified scheme, and Y a finite type scheme, also P an integer. So actually the segment is only non-empty when P is non-zero. Is bigger than zeros. Now let omega star star be star star a polytray which is generically integral over the following star-star scheme, which is okay. So here I wrote Bx to denote the pro scheme of all toroidal blow-ups of X. Okay. So for example, if X is an, this is just an hat or a hat I. Okay. And this is somehow the case I'm interested in, but just I said this a bit in a more general situation. And here also this is just the pro object of toroidal blow-up of V times X. Okay, so I'm saying, so I'm taking W star star, which lives over this and is generically integral over this star star scheme. Then also let V star star be inside W star star, a closed polytray. Okay, closed. And then let's fix a point in V11. Okay, so now we have the following. So then the conclusion is that we have that say the transcendence degree of the fraction field of this n plus V star star psi 0, 0 is bounded by 2p. Okay, so this is this is the statement of this theorem. As I said, this is somehow what, if you want, what justifies the construction of the Bloch-Levin tower, and somehow many things in the strategy is somehow, if you want, done in order to be able to use this fact. So why is this fact is useful for us? So remember, maybe let me make a remark. So let me remind you that last week that there was this argument using Hodge theory, which where we had somehow to have a bound on the dimension. So from last week, we saw that it is important to have a bound on the dimension of some schemes U, which were obtained by completing. We had these squares, and we were completing these by some U. This gives the category A x star star of some flag. And so we wanted some information about the dimension of this U that appears. Of course, the dimension somehow up to refinement. And so this theorem is saying that if you are interested in computing the cohomology, if you're interested in computing the cohomology of such a star-star scheme, then you only need to consider the values of your theory or complex of Pleshev on V star-star polytray, which are generically integral. But for these, we know that we can complete the diagram by U which have small dimension, and this is exactly because of this bound on the transcendence degree. All right, so I hope it's clear why this is an important fact. I don't know if you have a question. I could try to say more. But and so I will not prove this, but I'll try at least to prove somehow the simplest case of this, just to give you an idea what's happening. And in fact, it's for proving this theorem that somehow one also needs this moving lemma by blow up. But I will not be able to tell you how, because I will not give the proof. And the case I will consider will not need this lemma. Right, so as I said, do proof in the simplest case. And so what is the simplest case? This is when V is the spectrum of some extension, finitely generated extension of K. So generated extension, and X smooth with the with the coarse smooth with the coarse stratification, and also and also I want V to be the W star star to be a star point. Namely, something like x10, x11, x01. So this will be spec k. This will be a point in the extension of x to k, and this is a point of x. So I just explain what happened in this case. So what is the in this case the hypothesis is that x11 belongs to up xk, and the conclusion is that we want that the transcendence degree of kappa x10 intersected with kappa x01 is bounded by 2p, but in fact here one can show that it's bounded by p. And so this is we want to show this implication, and this is actually quite easy. Let me tell you how it works. So let me denote d the dimension of x, e the transcendence degree of this extension. All right. So the point is that the condition that the codimension x11 is smaller than p implies that the transcendence degree of kappa x11 is larger than d plus e minus p. Right? I mean, this is like scheme of dimension e. So xk is like a scheme of dimension d plus e, and I'm taking a point of codimension p. So this point has transcendence degree larger than d plus e minus p. Okay. Now, kappa x11 is generated by by k and kappa x01. And so we have that transcendence degree of kappa x11 is equal to e plus transcendence degree of kappa x01 minus transcendence degree of kappa x00. Okay, kappa x00 is the intersection. Right, so all right, so putting these two things together, we get that transcendence degree of kappa x00 is smaller than p minus d plus transcendence degree of kappa x01, which is smaller than p, as we want. Okay, so it's a very simple argument. It's a bit more involved when in the general situation, but the idea is essentially when it's somehow reduced to this kind of reasoning. It's actually maybe a good time to take a small break, and then yes.
Well, I have to leave maybe like 15 to 20 minutes. So.
In 15 to 20 minutes? Yeah, so anyway, I will not finish in 15 minutes. So yeah, I think we take 10 minutes break or 5 minutes break, and then yeah. Is it working? All right, so now we come to the final, I think it's final paragraph. I'll try to explain how we can conclude. This is 7.7. So this is computing the quotient of the homotopy limit that you are interested in. Okay, so let me remind you what we have. So we have a map from the homotopy limit of the Chow complex on the spectrum representing the Ram cohomology. So this goes to the homotopy limit of this pi star construction on some explicit T spectrum, which is G lower star, infinite suspension of Goldman complex of some chi dot some co-simplicial complex of flaggy presheaf, which was denoted by x dot Hodge, and this has to be made fibrant before applying G lower star. Okay, so we have this map, and now just obviously by the construction of the Bloch-Levin tower, I can go from here to a map to the homotopy limit of the associated complex of presheaf or the spectrum of the limit of the tower. So this will be homotopy limit Bloch-Levin tower star of exactly the same thing. So maybe I don't write it. And as I also mentioned at the beginning of the lecture today, in this particular context, this A is not really doing much. It's given by a homotopy colimit, but all the transition map are quasi-isomorphism. So in fact, one can put A, one can commute A and the homotopy limit. So you can put A here. And now I have two homotopy limits, and then I also can commute them. So okay. Now P is fixed, right? So now I somehow I concentrate on this guy here. So here now, so if I evaluate this at so if I fix level scheme X and I evaluate what happens here for a fixed P, then I can use the criterion from the previous section, which would tell me that in fact I don't need to know that I could replace my X by anything which has the same values at these star polytray, which are which are of some special kind. Okay, so let me try to say this more precisely. So in fact, yeah, maybe it's better to do it like this. Now, we also have, on the other hand, we have a filtration FD on this object. Remember, and this filtration is induced by filtering the category A by some FD A, so for various okay, so we remember, yeah. So there is a filtration on this category by the dimension of the target of U. Okay, and this filtration induces a filtration on these flaggy complexes of presheaves. Now if I want to compute the homotopy limit, or if I want just to compute just the Bloch-Levin tower at X, somehow the previous proposition, really the proposition from previous paragraph, tell me that in fact I can replace X by FDX for D big enough. Okay, is this clear, or should I try to explain this more? Is this clear? Maybe let me just say it once again. So if I fix X, so I can use the previous proposition and then also the previous theorem, which tells me that, in fact, for all the relevant, if I put here V star instead of X, for all the relevant polytray V star, we have, in fact, essentially equality of these two categories. Okay, because of the previous theorem. If X is fixed and P is fixed, and therefore I have now a bound on the dimension of the U which are relevant, and therefore I can use this argument from Hodge's theory, which then enables me to compute the homotopy limit. Okay, so by the argument from Hodge's theory, this homotopy limit for X fixed is the same as. So I can write it down. It's the Bloch-Levin tower of sigma T infinity Goldman complex, and now I just replace X dot by X minus 1. Right, so this is using the ingredient from Hodge theory. Yeah, we got rid of for the homotopy limit of the main homotopy limit. Yeah, yeah. So we computed in some sense we computed the homotopy limit. Okay, so we get, yeah, so let me again write it down. So we obtain, so by this reasoning, we have a map from the homotopy limit of Chech omega that goes to the associated complex of free sheaves or spectrum, or limit of the tower, the Bloch-Levin tower, okay, so this is what we have, and now the rest of the argument is to try to go from here to this thing. And so so this is constructed in few steps. So that we need, so this is constructed in few steps. So try to describe these steps. Okay, so step 1. So this is replacing chi minus 1 Hodge by a simpler complex. Laggy sheaves. Okay, so let me describe to you this simpler complex. Okay, so let us recall what is x minus 1, and then I can tell you what is the simpler version. So so x minus 1 Hodge takes it a fourth tuple I alpha x star d, and so it sends this thing to homotopy colimit of u of yeah, basically cohomology of u circ with value in mu, some module of logarithmic type over u circ. And so what we can do, there is an obvious map to something where there is no homotopy colimit anymore, and namely this is the Ram cohomology, the cohomology, I mean this is the derived double section, sorry, derived double section, not of u, but of something which is independent of u, namely this is m circ x10 d underline, and this is with value in the logarithmic, in the module of logarithmic type n, or maybe nd. Okay, so remember mu is really just the non-underived direct image of nd, and there is a natural map like this. And so this is what let's call this guy here just y of I alpha x star star nd. So this is again a complex of Flaggy presheaves, and obviously I can yeah, and there is a map, yeah, there is a map from x minus 1 to y, and I can replace here this thing by y. So this is the first step. Yeah. Yeah. How can I say this? So, I mean, you see much of the things are happening at 0, 1. For example, this. I mean, the construction. I mean, the SPI takes into account some affine spaces which are over 0, over 1, over 0, 1, and 1, 1. So most of the construction is happening on this side, and if you put it there, it's just too complicated. So it's better to have it on this side. And I mean, and this is used in step 2, which unfortunately I will not be able to really get into the proof. So it's maybe not clear how this is used, but it's really it's important in step 2. Sorry, say again, if there is.
Since you have a lot of construction on 1, 1 and 0, 1, I guess.
Yeah.
Like 1, 0, 2, 0, 1, 0.
Yeah, this is why it's I put it on 1, 0, exactly. Yeah. Okay, so and as I said, this is the reason why you put it on 1, 0 somehow is apparent if you try to get into the proof of step 2, which is a crucial step in some sense. This is where we somehow where we close the holes in the Bloch-Levin tower. So we somehow we put back somehow the closed subset that we have removed. So okay, so let me. So I try maybe to say at least orally how this enters. So let's see. Let's fix a scheme which is leveled. So finite type. And let's work. So we work at also at level m, but level m not level m in the sense of spectra. So here's a claim. Is that for p big enough, so with respect to x and m, so for p big enough, the map in the Bloch-Levin tower, so p lp plus 1 star evaluated at x to the same thing, is a quasi-isomorphism. All right, and so let me just very quickly just tells you what's going on here. So, okay, so this boils down to so-called purity in motivic cohomology. Which is the statement that if you look at motivic cohomology, let's say in degree Q, but in weight P, and you look at the restriction map to some open subset. So this is an iso if x minus u has codimension bigger than p plus 1. Yeah. So we want to apply this, of course, for p equal to m. Right? So we take p. So if p is m, this is, I mean, motivic cohomology with value in zp is just another notation for taking the I don't know, the étale cohomology, if you want, or Nistevich cohomology of x with value in T tensor M made A1 étale fibrant, for example. Okay. And so and here, so at the Bloch-Levin tower at p plus 1, we are removing closed subset of codimension bigger than p plus 2. Okay, and so it's I mean, it's not surprising that to prove such a thing, it's useful to have something like this. Now, of course, this is not so simple, and one complication comes from twisting by y, right? So twisting by y somehow destroy. You cannot just twist by any complex here and hope that this is still true. But now somehow, since y is coming, you see that there is this situation. So here we have 1, 0, here we have 1, 1, here we have 0, 1. So computing this, I mean, this is really something happening here, in the sense that you take an A1 fibrant replacement, maybe étale, and this is somehow only computed here. And since y is really coming from this side of the diagram, it doesn't interfere too much with motivic cohomology, and this is still true in somehow for this twisted version. Okay, and so this is the idea why we have this. So the Bloch-Levin tower, I mean, you can replace. I mean, you can replace this by motivic cohomology. You can put here if you want ZM. That doesn't matter. Now the Bloch-Levin tower, you have to remember the construction. So so this was constructed by somehow evaluating at these guys, UP, right? And these are the pro-opens that you obtain by removing closed subset of codimension bigger than p plus 1. So this is at level. This is below BLP. Here you are removing something which is of codimension bigger than p plus 2. And so this thing here pretty say that at some point it doesn't matter what you are removing, unless if it's of codimension big enough, it will give you the same answer. Right? So this telling us that this tower somehow stabilizes for p big enough. Okay, so what is the conclusion of this? The conclusion is that you can replace this the homotopy limit of the tower, of the Bloch-Levin tower, by the thing that comes just before in its construction. Namely, we get now a map from the homotopy limit of what we want to this version of the Suslin-Vygotsky complex. So by hat star G lower star infinite suspension chi of y h fibrant. And in fact, since this guy is fibrant, this is also the same as just pi star. The national map goes like this. Right, so this is step 2. Now step 3 is going back.
You did two steps in one.
Did I do this?
First line is already removing the colimit over P.
Yes.
Is that right? This says you can remove the colimit over P.
You mean the limit over P? Yeah.
Colimit.
Yeah.
Like as if I know the difference between a limit and a colimit.
Okay.
There was a homotopy limit
Yeah.
over P.
Right.
But that goes away because for P is
Exactly.
really large. So that's already one significant thing.
Yeah.
Using this purity.
Yeah.
That's on the first line.
Right.
But then what did you do on the second line?
Here you mean?
Second line.
Here.
Yeah.
Oh, this is okay. This is a lemma we have seen today. I don't know. So this is so this is essentially what you have when you go to the limit, right? So when you don't have any holes anymore.
Yeah, this is the version without holes.
Right. This is without holes. But then there are still these blow-ups.
Yeah.
Right? And this is a version without anything, without blow-ups. This is just the plain version, the simplest one. And this is a general fact. Whenever you have something which is fibrant, for the H topology, you have a quasi-isomorphism like this.
Oh, because it's fibrant for the
Exactly. Yeah. That gives this.
Yeah.
Okay. So, okay. Now it's step 3 is going back to. So it's a bit weird. One has to. I mean, I didn't find any way to do this. So one has to go back to foliations, and this is essentially somehow to get rid of the H topology. So again, I'll be very sketchy here and just say a few words. So here, the idea is that so by reversing some constructions. So I mean, before I was, if you remember, I had something which involved foliation, and I was spent some time to explain how one could get rid of foliation and write everything in a way which is completely algebraic. And here the step is somehow going back a little bit. So somehow it's like, I mean, there is maybe some tension. So it's either you work with foliation, and then you can have a topology which is not so bad. Or if you want to have something which is algebraic, you are forced to work with the H topology. And so somehow you cannot have both. And so, yeah, so somehow this step is, the goal of the step is to get rid of the H topology, and for this we need to go back to foliation. So I will not really explain how this works. I want to explain the construction of a version, if you want, of this Y, which involves only foliation and maybe the Psi et al. Topology, and for which we can find a map from Y to this. All right. So let me just do this construction. All right. So consider the morphism of site that as follows. So I call it E. So let's go from smooth foliations over the diagram E bar, theta bar, omega n. To the etal site of the same guy. Okay, so I endorse this maybe with the Psi et al. Topology. Okay. Now, let's see. I want to define. First, I want to define a complex of presheaves here, and then put it back here. So, let's see. Sorry. Can you say again?
I didn't remember what is
FT. So these are the foliation which are differentially etal over the base. Okay. So given. So let's fix I alpha in theta bar omega n, and x over f, which is diff et al. Over E bar alpha. Okay, and I want to associate to this some complex, which will obviously have to do with Y, and without proof, I will tell you then that you can replace Y by the thing here. Right. So remember that in this situation we have this associated map or quotient, universal quotient such that x is over E alpha 0. Okay, so this is the largest quotient such that the image of x in E bar alpha 0 is contained in the open E alpha 0. Okay, so right, and then we look at, so we have this torus E alpha 0, and there is also a well-defined quotient of, so this is a quotient of tori, which is again the largest one, such that if you look at E alpha 0 times AI, and you put this natural foliation structure on this. I don't know if you remember this. There is this exponential foliation which is on this product. And you look at the map projection to T, this factors through the discrete torus. Okay, so essentially, I mean, this is actually quite simple, and maybe it's a bit complicated the way I'm writing this. But so you see, yeah, essentially what I'm saying here is that if you look at the function which are in the kernel of the derivative, it will define to you a quotient which is a torus, and this is T. Okay, so there are many functions here which vanish by the differential of this foliation, and the subalgebra is just the algebra of a torus. All right, so with this, then we then set. So I define y prime, so I alpha x over f, by definition to be the R gamma delta of, so yeah, it's actually, yeah, let me write it like this. This is not correct, but doesn't matter. Okay, so it's the RAM cohomology. Yeah, actually, I don't want to take R gamma. I really want to take the RAM cohomology. I don't know. Let's just write it like this: omega. The RAM complex. Yeah. Yeah. Okay. If I want to be really correct, I should do it differently. Put a T here. All right. So let me explain what this means. So so this is a spectrum of what is it? Yeah. So you take OX and you go to omega of x times T delta. Right, so you look at the function here which are 0 in this product. So this defines to you an algebra over T which is differentially étal, and then you tensor it with T delta. Is this correct? No, I don't think this is. No, this is not right. Sorry, I have to do it. Sorry, it doesn't matter, I think, but just to be correct. So what you do, you look at xf, and you take E alpha 0. Again, so this is the same thing. You look at functions over x which are constant over over E alpha 0. You take the spectrum of this, so this defines to you an E alpha 0 diff étal foliation. Then you tensor this guy with T tensor T delta, and then you compute the drum cohomology with value in alpha. Okay, so it doesn't matter at all. Let me just state two things which really which somehow justify such a definition. So first is that we essentially still have a map. Yeah. So the right-hand side. So this is constructed in a way such that the right-hand side from this above maps to pi. Now there is no star anymore, but to pi of sigma t infinity of E upper star. Oh, there is a star. Let me put a star here. So this is now it's one has to work over I don't know, this part of the diagram. So we don't need any more this, but we still need so yeah. Okay, it doesn't really matter. Just let me. So we still have such a map, and the second important property is that so this guy here. So this is a foliation, and so the f dimension, so the dimension of the leaf, happens to be smaller than the cardinality of I minus 1. Okay, let me just explain this quickly. So yeah, I mean the point is that so this foliation here has dimension less than the cardinality of I minus 1, because it's differentially étal over AI, which is a smooth scheme of dimension cardinality of I minus 1. Okay, and yeah, and yeah, and by construction, I mean, in fact, this is not completely obvious, but one can show also that this guy, so the dimension of this torus of T is let's say is equal it's alpha 0 minus the cardinality of I minus 1 plus 1. Right, so what I'm saying here is that the map from here to here, the fiber of this map have dimension at most cardinality of I minus 1. Right, so this is really a big torus. And this has to do with the reason. This has to do with the choice of omega. In fact, so if you remember omega of I, this is a set of translate invariant one forms defined over Q. Okay, so this is. If you take coordinate, this is something. This is just dt1. This is a vector space over Q, generated by dt1 up to dtn. Okay, and because of this, you see that yeah, that so if you take a big number of such differential forms, then you can write most of them as linear combination of at most cardinality of I minus 1 of them. And because of this gives you this big torus. This creates a lot of constant, and you can show that this torus is big, and therefore we have this. So since the dimension of the fiber is bounded by the cardinality of I minus 1, And if you think about it, if you think about this for a moment, you see that this foliation has also a dimension like this. And in particular, this complex, y prime I alpha xf, has no cohomology in degree bigger than cardinality of I. So it's a bounded complex, and it's bounded in terms of the cardinality of I. All right, so now we are almost at the end. So, these two, I mean, this property here implies the following. Sorry, this implies that this complex here is -1 connected. So one has to look at this a bit carefully, but so one has to go back to the definition of this operation and so on. But from this boundedness of in the degree, you can check that this complex is indeed -1 connected, and then there is an obvious map to omega, and this -1 connectivity tells you that this map factors through the truncation. Right? And this gives you the map that is that we are looking for. Okay. I think this is all what I wanted to say. I hope you see what that this ends. Okay, and so.